From the car you're driving to the building you work in, our entire world is literally built from bent metal. But have you ever stopped to wonder how we take a totally flat sheet of solid steel and shape it with just unbelievable precision? Well, the answer is a marvel of engineering that's as powerful as it is smart. Let's break it down.
So, yeah, this is the big question for today, right? How do you combine this immense, crushing force with the kind of accuracy you can measure in fractions of a millimeter? It seems kind of impossible. But the answer lies in a machine that's both an absolute beast and surprising genius.
And the machine that pulls this off is the press brake. Honestly, it's one of the true unsung heroes of manufacturing. It's working behind the scenes, shaping the metal that ends up shaping our entire lives.
At its heart, the whole concept is actually pretty simple. A press brake uses a top tool, which we call a punch, to press a sheet of metal into a V-shaped bottom tool called a die. It's this perfectly controlled, carefully choreographed collision between the punch and the die that forges a perfect permanent bend.
And once you know what they do, you start seeing their work literally everywhere. The chassis of your car, structural parts in an airplane wing, the ductwork for your air conditioning, even the metal cabinet that holds the server delivering this to you right now, all of it was almost certainly bent on a press brake. Its versatility is just what makes it so fundamental. Okay, so how does this thing actually work? Let's get into the anatomy of the machine. And the best way to think about it is to imagine its key components as a highly coordinated team, where every single member has a critical role to play. First up, you've got the frame. This is the machine's skeleton, and its only job is to be incredibly, unbelievably rigid. Because think about it. If that frame flexes even a hair's width under hundreds of tons of force, that tiny error gets magnified in the final part, and your precision is ruined. So this skeleton has to be rock solid. Next, let's meet the muscle of the operation, the ram. This is the massive, powerful beam that moves up and down, delivering all that crushing force, but with incredible control. It is the engine of the entire process. And here we have the hands, the parts that do the actual shaping. The punch, which is attached to the ram, is what forces the metal down into the die below. The specific shapes of this punch and die duo are what determine the final angle and the radius of the bend. It's all in the tooling. Now, all that force is totally useless without accuracy, and that is where the back gauge comes in. This thing is a super high-precision, automated stop. The operator just places the metal against it, and boom. It guarantees the first bend on the first part is in the exact same spot as the last bend on the 1,000th part. It's the real secret to consistency. And finally, we have the brain that coordinates the whole team, the CNC controller. This is where that raw power meets digital intelligence. CNC, or computer numerical control, is basically a sophisticated computer that calculates all the forces, tells the muscle how far to move down to the micrometer, and makes tiny adjustments on the fly to guarantee a perfect bend, every single time. Okay, so we've met the team, we know the parts, but what are they actually fighting against? To really get it, we need to dive into the physics of what's actually happening to the metal itself when it's being bent. You see, on a microscopic level, every single bend is a battle of forces. When you bend a piece of metal, the inside of that curve gets squeezed together. That's called compression. And at the exact same time, the outside of the curve gets stretched apart, and that's tension. It's like this internal tug of war happening right inside the steel. So somewhere right between that zone of compression and that zone of tension, there's a theoretical layer that does, well, nothing. It doesn't get squished or stretched. It's called the neutral axis. And for engineers, knowing its precise location is everything. It's the key to calculating exactly how the material will stretch and deform. If you get it wrong, a complex part with 10 different bends just won't fit together, period. But here's the thing, metal is stubborn. After you bend it, it has this natural tendency to want to spring back towards its original flat shape. We call it springback, and it is the #1 challenge in precision bending. The machine has to be smart enough to see it coming and counteract it. And get this, it's not just the metal that moves. Under all that immense pressure, the machine itself can slightly bend. The ram can bow up and the bed can bow down, just a tiny little bit right in the middle. But over a long part, that tiny deflection is enough to make the angle in the center totally different from the ends, making the part completely useless. So, how do you solve that? With a truly ingenious solution called crowning. It's an automated system, usually a series of hydraulic wedges in the machine bed, that creates an equal and opposite upward curve. It perfectly counteracts the deflection in real time. It's a brilliant example of how modern machines literally fight physics with physics to stay perfectly straight. A 90-degree bend is 90 degrees everywhere. So we've got springback in the metal and deflection in the machine, two major physical hurdles. And that brings us to how modern technology, the real brains of the machine, tames these incredible forces. So there are basically three main ways to get the job done. Air bending is the most common. It's fast, it's flexible, but it has the most springback to deal with. Then there's bottom bending, which uses more force for higher accuracy. And finally, coining, which uses extreme force to literally stamp the angle into the metal. That gives you the highest precision with almost zero springback. A single bend happens in 4 lightning-fast stages. First, the operator positions the metal. Second, the ram comes flying down, then slows right before contact. Third, the active bending. That's the moment of truth, where the force is applied. And finally, decompression, where the force is released and the ram retracts. It all happens in just a matter of seconds. And this is where that CNC brain truly shines. It keeps both sides of the ram perfectly synchronized, down to the micron. It uses actual lasers to measure the angle while it is being bent and makes corrections in real time. It automatically calculates the exact amount of overbend needed to fight that pesky springback. And the result? A tolerance of plus or minus 0.2 degrees. I mean, for an aerospace part, that's the difference between a perfect seal and catastrophic failure. That is staggering precision. Now, this level of precision didn't just happen overnight. For our last section, let's take a quick look at the journey that took us from these simple, clunky machines to the intelligent benders that are shaping our world today. I mean, just look at this evolution. We went from raw mechanical power in the early 1900s to controllable hydraulics in the 50s to the digital precision of CNC in the 80s. And now we have ultra-efficient electric machines and even AI-assisted systems that literally learn and get more accurate with every single bend they make. It's amazing. At the end of the day, the story of the press brake is a journey from brute force to digital intelligence. It's not just a simple press anymore. It's a smart, self-correcting, automated system that quietly and efficiently builds the metal components that hold our entire world together. And this whole journey from raw power to refined intelligence really leaves us with a fascinating question to chew on. If this is what we can do with a humble sheet of steel today, what in the world are we going to build tomorrow?